Episode 12 ended with one more concurrency problem. A user changes how many pods checkout app should run. The controller updates how many pods are actually available. At the same time, another automation adds metadata. All three changes are valid, but they are being written to the same Kubernetes object. So the question is, who should manage which fields, and how should each actor make its change safely? Before we go further, let us make Checkout App more concrete. In our example, Checkout App is a custom Kubernetes resource that represents the application we want our controller to manage. Just like other Kubernetes objects, it has metadata, spec, and status. Its spec describes what we want, such as how many replicas should run, while its status tells us what the controller currently observes. Now the responsibilities become clearer. The user or GitOps system decides the desired replica count and spec. The controller reports what it actually sees in status. And an automation may manage a particular label and metadata. Sharing one object is not automatically dangerous. The trouble starts when one writer sends or changes fields that belong to somebody else's responsibility. Let us first see how a normal update works. The client reads Checkout App and gets the latest copy of the object, along with its resource version. It then changes the field it needs to update. After that, it sends the object back to the API server using a PUT request. So the basic flow is simple: read the object, make the change, and send the updated version back. The resource version still protects us from using old information. Suppose the client reads Checkout App at version 900. Before it sends its update, another writer changes the object, so Kubernetes moves it to version 901. Now the first client is working with an older copy. If it tries to update the object using version 900, the API server rejects the request with a conflict. This prevents an old update from accidentally overriding a newer change. But a full update can still create another problem. Suppose the controller only wants to say that 3 replicas are currently available. The object it sends back also contains other information, such as the desired replica count and metadata labels. Those fields may be managed by someone else. So even though the controller only wants to change status, it ends up carrying many unrelated fields in the same update. That makes different writers depend on each other more than necessary. Think of this like a shared form with 3 sections. One section says how much capacity we want. Another says how much capacity is currently available. A third contains business labels. If the controller only wants to change current capacity, why should it photocopy and resubmit the entire form? It would be safer to send only the box that actually changed. That is the idea behind patch. An update sends an object representation back. A patch sends the change you want the API server to make. So when a writer owns only a small part of a large object, a targeted patch can avoid touching unrelated fields. Suppose the user wants Checkout App to run 5 replicas. The user does not need to send the controller's status or every metadata field. The request can target the replica field in spec. The change says, make spec.replicas equal 5, and leaves unrelated parts of the object alone. The metadata automation can do the same thing. If its job is to add a cost center label, it can patch only that label. It does not need to send spec or status. Now 2 independent writers can make small changes without carrying large parts of the object they do not own. Kubernetes supports several kinds of patch, and we do not need to memorize all of their syntax here. JSON patch describes operations such as add, replace, or remove. JSON merge patch describes a partial structure to merge. Strategic merge patch adds Kubernetes-aware merge rules for supported built-in types. And server-side apply adds declarative field management, which we will use shortly. But a small patch does not answer who owns the field. Imagine two actors both patch spec.replicas. One wants 5 replicas and the other wants 8. Both requests are small, but they still disagree about the same field. So after reducing the size of the write, we still need a way to describe responsibility. Before solving field ownership, there is one boundary Kubernetes already understands very well: spec and status. Spec says what we want, for example, 5 replicas. Status says what the controller currently sees, for example, 4 replicas available. One is desired state, and the other is observed state, so they naturally belong to different writers. For resources that expose a status subresource, Kubernetes gives status its own write path. Normal writes go to the main resource. Status writes go to the same resource name followed by /status. This lets the controller report observed state without behaving like the owner of the whole object. Think of it as one building with 2 controlled doors. The configuration door is used for the desired configuration. The status door is used for what the controller has observed. Both doors lead to the same Kubernetes object, but each door limits which part of that object the request is allowed to change. The boundary is enforced by the API server. When the status subresource is enabled, a write to the main resource does not update the status section, and a write through /status does not change spec or normal metadata. So a controller writing status cannot accidentally change the user's desired replica count through that status endpoint. Permissions can make that boundary even stronger. The user or deployment pipeline can be allowed to update the main resource. The controller can be allowed to update the status subresource. That means we are not relying only on good behavior. We can give each actor permission to write only the API path it actually needs. Now replay the user and controller changing checkout app at nearly the same time. The user changes spec.replicas from 3 to 5 through the main resource. The controller changes available replicas from 2 to 3 through /status. The changes have different meanings and use different write paths, so the controller does not need to rewrite the user's desired state. The automation still needs to add a label. It can use a targeted metadata patch and avoid sending either spec or status. So our 3 writers now have much cleaner behavior. The user changes spec, the controller writes status, and the automation patches only the metadata it needs. But there is still one case we have not solved. What if 2 declarative systems both believe they manage the same field? For example, one says the environment label should be production, while another says the same label should be staging. A smaller patch cannot tell us which workflow is actually responsible for that field. Server-side apply adds that missing idea. Each apply request identifies the workflow making the request with a field manager name. For example, one request may identify itself as GitOps and another as platform automation. The request describes the fields that workflow intends to manage, and the API server records that relationship. Kubernetes stores field management information in metadata.managed fields. You can think of it as a map of which workflow currently claims which fields. For example, GitOps may manage spec.replicas, platform automation may manage a cost center label, and the checkout controller may manage available replicas through the status subresource. This works well when managers are responsible for different fields. GitOps can apply the desired replica count. Platform automation can apply its cost center label, and the controller can report available replicas. The object is shared, but the responsibilities are explicit, so these changes can coexist instead of fighting over the whole object. Now suppose GitOps already manages spec.replicas and says the value should be 5. Another server-side apply manager tries to set that same field to 8. Kubernetes can see that the field already belongs to a different manager with a different value. Instead of quietly overriding it, the apply request is rejected with a field conflict. This field conflict is different from the resource version conflict we saw earlier. A resource version conflict means I tried to update the object using an old copy. A server-side apply conflict means I am trying to change a field that another manager claims. One protects a read-modify write from stale object state. The other exposes competing responsibility for a particular field. When Kubernetes reports an apply conflict, it means two workflows are trying to change the same field. We should not simply force our change through. First, we should check which workflow is supposed to manage that field. If the other workflow should remain in control, we leave it alone. If our workflow should take over, we do that intentionally. So the conflict is really Kubernetes telling us two managers are trying to control the same field. We can now build a practical decision model. If you truly need to replace a known whole object, use update and its resource version. If you only need to change a small part, use a targeted patch. If a controller is reporting observed state, use the status subresource when the resource provides it. And if a declarative workflow is responsible for selected fields, server-side apply can make that field responsibility explicit. Now replay the problem that started this episode. GitOps changes the desired replica count from 3 to 5. The controller updates available replicas through /status. The metadata automation adds its cost center label with a targeted write. This time, each actor changes only its own responsibility, so all 3 changes remain in the final object. When a field changes unexpectedly, this gives us a much better debugging method. Check whether the request was an update, patch, or apply. Check whether it used the main resource or /status. Look at resource version conflicts, the field manager, and managed fields. Then ask which exact field changed and which workflow sent that request. That tells us whether the problem was stale state, a broad write, the wrong API path, or a real ownership conflict. The engineering rule is now simple. Use the smallest safe write, use the correct subresource, and make field responsibility explicit when several declarative writers share an object. In other words, each actor should write only the fields it is responsible for through the narrowest safe API path. There is still one more question. Suppose the user changes checkout app from 3 replicas to 5. At the same time, the controller is finishing an earlier check that started when the desired count was still 3. The controller may now write a status update saying that 3 replicas are available. That status is not necessarily wrong, but it may describe the older desired state. So how can we tell whether the status has caught up with the latest change? In the next episode, we will see how metadata generation, observed generation, and conditions help Kubernetes answer that exact question. Is the status we are reading about the latest desired state, or is the controller still catching up?